tricky. I'm sure numerically you could do it, but with numerical approximations, but I don't know about exact forms.
Thanks. So this is joint work with Santosh Vimpala, Georgia Tech. What I want to do here is take some small steps towards trying to understand what's going on when we train neural networks using gradient descent. And in particular, we're going to give matching upper and lower bounds for learning polynomial concepts. The upper bounds are for a simple model of gradient descent for neural networks. The lower bounds are for any SQ, any statistical query algorithm. So the simple model in which we prove our upper bound is for a single hidden layer neural network. The inputs are drawn uniformly from the sphere. The hidden layer weights are also uniform from the sphere. You take a essentially arbitrary activation unit in the hidden layer and a linear output. We don't have any additive bias terms here in order to sidestep some earlier lower bounds. And the goal here is to minimize mean squared loss using gradient descent. In this particular form of gradient descent, we're going to be reusing the entire example set in each iteration, and we update only the outer weights using a fixed learning rate. So this updating only the outer weights using gradient descent transforms this into a convex problem. The convexity is not really important for analysis, but we don't need to update the hidden layer weights because it already meets the lower bound in this setting for the learning polynomials that we care about. So this is just the simplest setting in which we can display the proof techniques that I want to show you. So what's the result? So if you want to learn some concept over the sphere up to an additive error epsilon, compared to relative to the best degree k polynomial approximation for your concept, then you can do so in time n to the k using n to the k units in your neural network and n to the k examples. This is stated here for sigmoid activation functions, which are essentially odd except for the degree 0 part. But this generalizes then to arbitrary activation functions and non-odd functions. There's a host of related works here, and I don't really have time to go into the details of all of them. Some of them, for example, consider algorithms other than gradient descent or other families of concepts. I do want to mention explicitly the work of Andoni Panigrahi, Valiant, and Zhang from 2014 that also studied learning polynomials via training a neural network by gradient descent. Compared to that paper, this result is agnostic, has a better iteration bound logarithmic in the error instead of polynomial. But more importantly, it's a nice proof. It's a pretty proof with some useful direct consequences that come out of the particular method of analysis. And in particular, one thing that we're able to show as a consequence of our analysis is to provably establish a spectral bias phenomenon when training neural networks via gradient descent. So this was a phenomenon that was observed empirically in a couple of papers this past year. And essentially what this spectral bias phenomenon says is that when you train a neural network by gradient descent, you pick up the lower frequencies of your concept before the higher frequencies. So for example, in the Fourier transform of your concept. And this was observed empirically, and it's a possible, sort of plausible explanation for the generalization capability of deep learning, because you might think that lower frequencies represent more stable patterns, higher frequencies are more likely to correspond to just noise that you don't want to learn. And we prove that this phenomenon, in fact, occurs. Specifically, what we show is that if you look at the error in your residual in degree k relative to degree L, so in our sense, learning functions over the sphere, the relevant concept of a frequency is the degree of the corresponding harmonic expansion. So what we show is that the relative error, the the improvement in the relative error in degree k relative to some degree L is a factor of n to the L minus k, where k is the lower degree, L is the higher degree, after normalizing for the amount of error present in the residuals. So what this looks like is, you very quickly learn lower degrees. It takes a much longer time to learn higher degrees. So in this figure here, time is going from left to right over multiple training iterations. Blue corresponds to a low value, orange to a high value. Okay. So how do we prove these results? So we use some tools from harmonic analysis, in particular the classic Funk-Hecke theorem, which characterizes the eigenspaces of a particular operator on functions. So this is the Funk transform here. It has a very natural form. Given a function on the sphere, I take its average against some activation function applied to a dot product. And what the Funk-Hecke theorem says is that the eigenfunctions of this operator are exactly the degree k harmonic polynomials. And furthermore, we can compute the eigenvalues. And for example, for the sigmoid activation function, these eigenvalues are of the form n to the minus k for odd k and 0 for even k. Okay, so how does this appear then in our analysis of gradient descent? Okay, so here's just an illustration of what the Funk transform is doing. I have my original function on the left and the Funk transform of it on the right. So this is a function on S1. The orange color corresponds to positive values, the blue color to negative values. So this is a function given by the sum of a degree 1 part and a degree 4 part. And you can see that the Funk transform preserves the degree 1 part, preserves the degree 4 part up to some scaling. It shrinks, it scales down the higher degree part more than the lower degree part. So this is all the Funk transform is doing. So how does this show up in our analysis of gradient descent? Well, if I look at the empirical gradient operator, so the gradient operator using a finite set of samples, this has essentially the same form as the Funk operator. It's essentially the finite sample version of the Funk operator. But you'll notice that it's also essentially the same form as a single, the function computed by a single layer neural network. So the way we perform our analysis is to show that this empirical gradient operator is a good approximation for the Funk transform. We bound the rate at which the error of that approximation accumulates over multiple rounds of gradient descent, and then we're able to in a very straightforward way, estimate the final loss that we obtain in terms of the distance to the most significant eigenspaces using the Funk. Okay. So the lower bounds that we prove are in this statistical query framework, with which many of you will be familiar. In this framework, the algorithm can do whatever it wants, except that it doesn't have access to the labeled examples. Instead, it has to query an oracle, gives the oracle some function, and the oracle responds with the expected value of that function over the labeled data distribution up to some error tolerance tau. What we show is that in the SQ framework, there are families of size d of degree k polynomials on the sphere Sn, so that if you want to learn these using a randomized SQ algorithm, you'll need order of d queries, where the queries have tolerance of the order n to the minus k. And this compares then to an information theoretic lower bound of log d, so this is sort of an exponential gap there. And there are lower bounds then also for the honest one-stat, oracle, and other query models. So in the SQ framework, if you want to understand gradient descent in terms of these statistical queries, the queries that you're making to your oracle are, for example, the gradients. So what this is saying is that for these polynomials, you anyway need this number of samples that matches our upper bound. Okay. So I want to mention some sort of open problems going forward. So these are sort of some pleasant techniques that we use in our analysis. Can we understand more general phenomena in deep learning using these tools? Are there other SQ lower bounds that we can obtain for regression problems? This is the second paper now that's looked at regression problems in this SQ framework, and there are some sort of complications that arise here. Or, for example, for deep but low-ranked neural networks instead of these shallow but high-ranked neural networks.